Space itself is stretching, and it will decide the fate of everything. This is not a theory, but the measured reality of our cosmos, where the expansion of space dictates the ultimate destiny of every particle of matter and every ripple of energy. By the end of this journey, you will understand the final forecast for the universe itself, from the silent fade of starlight to the profound transformation of reality. We will confront how black holes could simply evaporate and why the very atoms in your body might not last forever. What do you believe remains when the universe grows cold? That loaf of bread is still baking, and it has been for almost 14 billion years. The key to understanding this cosmic stage came from a man named Edwin Hubble, who peered through the Great Telescope at Mount Wilson and noticed something profoundly unsettling. The light from distant galaxies was not what it should be. The specific colors, the unique fingerprints of elements like hydrogen and helium, were all systematically shifted toward the red end of the spectrum. It was as if the very notes of a cosmic song were being stretched into lower, deeper pitches. This was not a trick of the light or a property of the galaxies themselves. This cosmological redshift was a message written in stretched light, telling us that the galaxies were moving away. The farther away a galaxy was, the faster it seemed to be receding. This discovery shattered the old idea of a static, unchanging universe. It revealed a cosmos in motion, a stage that was actively growing. But here is the most crucial point, the one that changes everything about our story. Those galaxies are not simply flying apart through a fixed, empty space like shrapnel from an explosion. That is an easy picture to hold in your mind, but it is the wrong one. The space between the galaxies is itself stretching. Imagine two ants sitting on a perfectly stretchy rubber band. If you slowly pull the ends of the rubber band, the ants are carried apart. They are not walking away from each other. The ground beneath them is actively expanding. This is what is happening to our galactic raisins in the cosmic dough. Space itself, the fabric of reality, is being stretched. This intrinsic stretching of the stage is the engine of cosmic destiny. It dictates how light travels across the eons, turning brilliant blue starlight into faint, weary infrared. It governs how matter clumps together under gravity, fighting against this relentless pulling apart. It even influences the flow of time on the grandest scales. With this dynamic stage now set, we have to ask the obvious, thrilling question: who or what is pulling on the rubber band? What unseen force is driving this expansion, and is it getting stronger? The answer to that question arrived in the late 1990s, and it was not what anyone expected. Two independent teams of astronomers were observing distant stellar explosions called Type 1, a supernova, using them as cosmic mile markers to measure how the expansion rate had changed over billions of years. They were fully expecting to confirm that the pull of gravity, the collective tug of all the matter in the universe, was putting the brakes on the expansion, gradually slowing it down. What they found instead sent a shockwave through cosmology. The expansion of the universe was not slowing down, it was speeding up. Something was actively pushing galaxies apart, overwhelming the relentless pull of gravity. This mysterious something earned the name dark energy. Think of it as a property of empty space itself. Imagine the vacuum between stars and galaxies is not truly empty, but seething with a faint, uniform energy. This energy has a bizarre property. It exerts a negative pressure, a kind of cosmic repulsion. And because it is a property of space, as the universe expands and more space comes into existence, the total amount of this repulsive dark energy increases. This creates a runaway feedback loop. More space means more dark energy, which pushes for more expansion, which creates more space. It is the ultimate cosmic engine, and it is winning the battle against gravity. The implications of this accelerating expansion are profound for the fate of matter and energy. As space stretches faster and faster, distant galaxies will eventually be carried away from us at speeds that exceed the speed of light. This does not violate Einstein's rules because it is space itself moving, not objects moving through space. The light from those galaxies struggling against this stretching fabric will become so redshifted, its wavelength stretched so immensely that it will fade from our view entirely. The universe will not just grow cold, it will grow profoundly lonely. Galaxies beyond our local group will vanish over the cosmic horizon, their light never to reach us again. Our observable universe will shrink to an island of a few gravitationally bound galaxies, adrift in an endless, dark, and ever-expanding void. The nature of dark energy remains one of the deepest mysteries in all of science. Is it simply a constant energy of the vacuum, what Einstein called the cosmological constant, a fixed feature of empty space? Or is it a dynamic field that could change over time, perhaps even decay? The answer to this question is everything, because dark energy is now the primary architect of our cosmic future. It holds the steering wheel, dictating the long-term expansion rate, and therefore the ultimate destiny of every galaxy, every star, and every particle. But if dark energy is the force relentlessly stretching the stage, then matter, bound by gravity, is the actor trying to hold its ground. And that sets the scene for a dramatic, drawn-out conflict that will shape the next trillion years. Against this accelerating tide of dark energy stands the second great player in our cosmic drama, the collective gravity of all matter. This is not a simple force, but a partnership between the familiar and the utterly mysterious. On one side, we have ordinary matter, the protons, neutrons, and electrons that form every star, every planet, and every atom within you. Its gravity is the glue of our local reality, holding Earth in orbit around the Sun and our Sun within the Milky Way. But ordinary matter is only a small fraction of the story, perhaps just 5% of the universe's total mass and energy. The true gravitational heavyweight is its invisible partner, dark matter. We cannot see it, touch it, or directly detect it with our instruments because it does not interact with light at all. Yet we know it is there by the way its immense gravity bends the paths of starlight and dictates the very rotation of galaxies. Without dark matter's powerful, unseen grasp, galaxies would simply fly apart, their stars scattering into the void. Together, ordinary and dark matter weave the large-scale structure of the cosmos. Picture a vast, three-dimensional spiderweb shimmering across billions of light years. The strands of this cosmic web are immense filaments and halos of dark matter, a gravitational skeleton laid down in the earliest moments of the universe. Galaxies form like glittering beads at the densest knots where these filaments intersect, drawn together and held in place by the relentless, inward pull of gravity. This is the grand tug of war that has shaped the universe we see today. For billions of years, gravity has been the dominant architect, patiently gathering matter into galaxies and gathering galaxies into immense clusters. But the game has changed. As the universe expands, the average density of all matter, both ordinary and dark, steadily decreases. Think of ink dropped into an ever-growing bowl of water. The color becomes more and more faint, more diluted. As matter thins out, the gravitational attraction between distant structures weakens. Over cosmic distances, the gentle but constant push of dark energy now finds less resistance. The balance of power is shifting. While gravity will forever bind our local group of galaxies into a single, isolated island, its influence has limits. On the very largest scales, across the voids between superclusters, dark energy's repulsive push is already winning. This means the grand cosmic web, that beautiful, intricate structure, is not permanent. It is a transient masterpiece, The filaments will stretch and eventually snap. Galaxies on the outskirts of clusters will have their gravitational ties severed, drifting away into the expanding darkness. We are witnessing the peak of cosmic structure, a golden age of galactic gatherings that will not last forever. This slow dissolution sets a timer on the universe as we know it and forces us to ask a deeper question about the actors on this stage. If dark matter is the invisible scaffolding and ordinary matter is the visible building, what is the ultimate fate of the building blocks themselves? Can the atoms that form stars and planets, the very substance of reality, withstand an eternity of relentless expansion? That single photon's journey is the story of light itself in an expanding universe. It begins its life as a brilliant, energetic flash, perhaps in the furious heart of a young galaxy. It streaks across the void, a messenger carrying information across the ages. But the space it travels through is not a static stage, it is a stretching fabric. As the photon moves, the space between its wave crests is literally being pulled apart. This stretches its wavelength, shifting it from the blue end of the spectrum toward the red. This is cosmological redshift, and it is far more than a color change. It is a slow, irreversible draining of energy. The photon is not slowing down. Light always travels at the same ultimate speed. Instead, its intrinsic vigor is being diluted by the expansion of space itself. Think of a single, powerful shout echoing across a canyon that is constantly growing wider. The sound does not slow, but by the time it reaches the far wall, it has faded to a whisper. That whisper is the fate of all light traveling the cosmic distances. Over timescales that dwarf human history, this process transforms the very nature of radiation in the cosmos. The most violent high-energy gamma-ray burst, a detonation that outshines entire galaxies, will not remain so fierce. As its light voyages for billions of years through the stretching void, its wavelength will be elongated, its energy sapped. That cataclysmic signal will first soften into X-rays, then into harmless ultraviolet, then into the visible light our eyes can see. Its journey of dilution continues, fading through infrared into the domain of microwaves and eventually into the long, lazy waves of the radio spectrum. Every brilliant point of light in the distant universe is on this same inevitable slide toward a faint, cold whisper. This is why astronomers need such powerful telescopes. They are not just looking far away, they are listening for whispers from the past, whispers that have been stretched and faded by the expanding cosmos. But in an accelerating universe, dark energy adds a cruel, final twist to this story. Because the expansion is speeding up, there will come a point for any galaxy beyond our gravitationally bound local group where the space between us is stretching faster than light can cross it. The photon from that galaxy, no matter how long it travels, will never reach us. Its wavelength will be stretched not just to radio lengths, but effectively to infinity. From our perspective, that galaxy will have vanished over the cosmic horizon. Its light will have redshifted into complete oblivion, carrying its last signal into a form we can never detect. This is not a simple dimming, it is an information blackout. The universe is not just growing dark, it is growing silent. The consequence is a profound and permanent isolation. Imagine a future trillions of years from now for any civilization that might arise within our merged Milky Way and Andromeda galaxy. Their astronomers will peer into the heavens with technology beyond our dreams. But their telescopes will see nothing but blackness beyond the stars of their own galactic island. The cosmic microwave background, the faded afterglow of the Big Bang, will have redshifted into undetectable wavelengths. All evidence of the expanding universe, all clues to the vast cosmic web that once existed, will have vanished. The night sky will be a local affair, a beautiful but fundamentally lonely vista. The concept of an observable universe will have shrunk to the boundaries of gravity's local hold. severing the connective threads of light that once tied the cosmos together into a single, knowable whole. This silent fate awaiting light forces us to confront the durability of matter itself. If the messengers of the cosmos are doomed to fade, what happens to the things they once illuminated? Can the atoms that form the very fabric of stars and planets withstand an eternity of this relentless, accelerating expansion? The fate of matter is written in the life and death of stars. For trillions of years within the isolated islands of gravitationally bound galaxies, the familiar cosmic cycle will continue, but under a darkening sky. Stars will still ignite within lingering clouds of hydrogen, burning for billions of years before ending their lives in spectacular supernova or quiet planetary nebulae. These deaths are not an end but a transformation, seeding space with heavier elements forged in stellar cores. Yet this cycle has a final chapter. The primary fuel for new stars, the diffuse hydrogen gas that permeates the space between stars, is finite. As galaxies like our future merged Milky Way and Andromeda system consume this gas, the rate of star birth will slow from a roaring fire to a faint, sputtering candle. The brilliant, short-lived blue giant stars will vanish first, their furious fuel consumption leaving them as relics of a brighter age. The cosmos will become a gentler, redder place. The dominant stars will be red dwarfs, small and frugal, burning their hydrogen so slowly that their lifespans stretch for tens of trillions of years. To a distant observer, a galaxy in this era would appear as a soft crimson smudge, its fierce blue-white light long since faded, but even the most frugal star has a limit. One by one, over timescales that numb the mind, these last embers will also exhaust their fuel. A red dwarf does not die in a cataclysm, it simply cools, dimming over eons into a black dwarf, a cold, dark sphere of degenerate matter. This marks the end of the stellar era. The galaxy will no longer be a place of light and fusion. It will become a cosmic graveyard, a dark museum of stellar remnants. Drifting through this permanent night will be the cold, dense relics, white dwarfs, the Earth-sized cores of sun-like stars, slowly radiating away their last heat over eons longer than the current age of the universe. Neutron stars, the ultra-dense city-sized cores of massive stars, will spin silently in the darkness, and of course, black holes will loom, their event horizons marking points of no return in an already lightless void. Orbiting these remnants will be the frozen, dark planets, their surfaces receiving not a single photon of warmth from a host star. The dynamic, vibrant galaxy we know, with its spiral arms and stellar nurseries, will have transitioned into a simpler, darker, and profoundly quieter phase. This stellar twilight forces a startling realization. In this future, the only significant sources of energy in the entire galaxy will no longer be nuclear but gravitational. The final flickers of light and the last great releases of energy will come not from fusion, but from decay, from the slow, inevitable dance of these dark remnants under the unyielding law of gravity. But even the black holes, those ultimate symbols of gravitational permanence, will not last forever. Stephen Hawking delivered one of the most profound insights in modern physics when he revealed that black holes are not truly black. At the quantum scale, right at the precipice of the event horizon, pairs of particles and antiparticles can spontaneously flicker into existence from the energy of the gravitational field. Normally, these pairs annihilate each other almost instantly, returning their borrowed energy to the vacuum. But if this dance happens right at the edge, one particle can fall into the black hole while the other escapes into space. To an outside observer, it looks as if the black hole itself is emitting a faint, ghostly glow of radiation. This is Hawking radiation, and it comes with a staggering cost for the black hole. To preserve the laws of physics, the energy for creating the escaped particle must be paid for by the black hole's own mass. So, slowly, imperceptibly, a black hole evaporates. It loses mass particle by particle over timescales so vast they defy comprehension. For a black hole with the mass of our Sun, the evaporation process would take about 10 to the 67 years, a 1 followed by 67 zeros. That is so many orders of magnitude longer than the current age of the universe that it might as well be eternal from our perspective. But in the deep, dark future of a stellar graveyard galaxy, time is the one resource in limitless supply. One by one, over epochs we cannot truly grasp, even the stellar mass black holes will begin to fade. Their event horizons will slowly shrink as they radiate away their substance. The final moments of a black hole's evaporation are theorized to be a sudden, brilliant flash of energy, a last burst of particles and radiation as the remaining mass converts completely into light. Yet, in the accelerating universe shaped by dark energy, this final flash faces a cruel fate. The space surrounding the evaporating black hole is not static, it is stretching at an ever-increasing rate. The brilliant burst of energy, instead of illuminating a nearby celestial neighborhood, is immediately diluted, its photons stretched and redshifted as they travel. That final, defiant release of energy does not warm a single frozen planet or ignite a new star. It simply joins the cold, uniform background of an expanding void, its signal fading into the same oblivion that claimed the light of distant galaxies. This highlights the overwhelming influence of the expansion. Even the most formidable objects, the ones born from the most violent gravitational collapses, are not permanent structures in an accelerating cosmos. They are temporary knots in the fabric of spacetime, destined to eventually unravel, their transformed energy lost to the vast, growing emptiness. So if black holes, the ultimate sinks of matter and energy, can dissolve, what does that mean for the most fundamental building blocks of reality itself? Could the very atoms that make up the cold stellar remnants and frozen planets also face a final decay? The durability of an atom is the ultimate question for a fading cosmos. For all of human history, we have considered the proton, the positively charged heart of every atomic nucleus, to be a permanent fixture of reality. It is the anchor of matter, the unyielding foundation upon which the periodic table and the chemistry of life are built. Our best model of particle physics, called the Standard Model, treats the proton as perfectly stable, destined to outlast every star and black hole. But when we project our gaze across the truly cosmic timescales we have been discussing, spanning not billions but many trillions upon trillions of years, even this foundational certainty begins to waver. Many of the theories that attempt to unify the fundamental forces of nature, frameworks known as grand unified theories, suggest a startling possibility. The proton may not be eternal. It may possess an almost unimaginably long but finite lifespan. These theories predict that a proton could spontaneously decay, breaking apart into lighter particles like a positron and a pion, which would then quickly decay further into bursts of gamma-ray energy. The proposed half-life for this process is staggering, on the order of 10 to the 34 years or even longer. To grasp that scale, consider that the current age of our universe is only about 10 to the 10 years. A proton's potential lifetime is a number with 24 more zeros after it. It is a timescale so vast that in all the universe, across all of human observation, we have never seen a single proton decay. Our most sensitive experiments have placed detectors deep underground, shielded from cosmic rays, watching vast tanks of pure water for the telltale flash of light that would signal a proton's demise. So far, silence, the proton has proven stable for at least 10 to the 34 years, which is both a testament to its endurance and a hint that if it does decay, it happens on a timeline even more epic than we can currently probe. But in the deep future of a dark energy-dominated universe, time is the ultimate resource. Imagine a moment far beyond the era of black hole evaporation, when the cosmos is an expanse of profound darkness and near absolute cold. The only objects remaining are the cold, dark cinders of stellar remnants, black dwarfs and neutron stars that have cooled to just microdegrees above absolute zero. Orbiting them are planets that are no longer rocky worlds but cold spheres of iron, the final, stable end product of stellar nucleosynthesis. In this frozen, silent museum, the clock still ticks. And according to these grand unified theories, within the iron heart of a dead planet or the degenerate matter of a stellar corpse, a single proton in an atomic nucleus may suddenly, without cause or warning, cease to exist. It would vanish in a quiet flash of energy, transforming into radiation and lighter particles that quickly dissipate into the cold void. This would not be a violent explosion, but a slow, quiet unraveling of matter itself. One proton decays, then another a cosmic eternity later. Over these incomprehensible epochs, the very fabric of the last material structures would dissolve. An iron planet would not crumble, it would simply, gradually turn to light. Its mass would be converted, proton by proton, into a faint, diffuse glow of leptons and photons. This process, if real, represents the most fundamental erasure possible. It is not the gravitational unbinding of a galaxy or the evaporation of a black hole. It is the transformation of baryonic matter, the ordinary stuff of stars and planets and people, into its most basic energetic components. The last solid forms in the universe would fade away, not with a bang, but with a silent, particle-by-particle sigh into radiation. The cosmos would be simplified to its most elementary state, a thin, cold soup of photons, neutrinos, electrons, and positrons, drifting ever farther apart in the endless, accelerating expansion. This speculative fate forces us to confront a profound philosophical horizon. If even the atoms themselves are not forever, what, in the end, truly remains? Is there any structure, any pattern, any constant that can withstand the relentless tide of time and expansion in our universe? The universe settles into a profound and enduring silence. This is the era of black dwarfs and degenerate remnants, a chapter so long it makes the entire history of stars and galaxies seem like a brief, bright spark. A black dwarf is what remains when a white dwarf, the Earth-sized core of a sun-like star, has finally radiated away the last whisper of its residual heat. After quadrillions upon quadrillions of years, it cools to a temperature barely above the absolute cold of the expanding void. It is no longer a glowing ember, but a dark, crystalline sphere, likely composed of carbon and oxygen, its structure ordered into a kind of cosmic diamond, cold and inert. These dark cinders, along with the equally cold neutron stars and the frozen iron husks of dead planets, are the final monuments of the stellar age. They drift through the immense and growing voids, isolated islands of degenerate matter. Gravity still tugs at them, of course. Over these unimaginable timescales, occasional close encounters or collisions are statistically inevitable. Two black dwarfs might slowly spiral together over eons, finally merging in a flash of light as their carbon reignites in a final, feeble burst of fusion. A neutron star might be perturbed from its lonely path and collide with another, sending ripples of gravitational waves through the fabric of space-time. But these events are the rarest of cosmic accidents in an ever more empty theater. They are final, sputtering coughs in a darkness that has long since forgotten the roar of stellar furnaces. No new stars will be born from these encounters. The universe has become far too diffuse, too cold, and too old. The primordial hydrogen fuel is long since locked away in these dark remnants or diluted into a near-perfect vacuum by the relentless expansion. Nuclear fusion, the engine that powered the cosmos for trillions of years, has run its course and shut down permanently. This epoch represents a strange, bleak equilibrium. Matter has reached its most stable, inert, and compact forms. It is a museum of cosmic history where every exhibit is dark and silent, a frozen archive waiting under a black sky. Time continues to pass in magnitudes we cannot truly fathom, but on a cosmic scale, very little happens. The universe is not yet empty, but it is functionally asleep, with matter existing in a state of near-permanent rest, awaiting the next set of rules to take effect. The only active player left on this vast stage is the expansion itself, the silent, relentless stretching of space that continues to pull these dark remnants ever farther apart, diluting even the faint possibility of future collisions. In this profound stillness, we are left to wonder, is this the final state, a cosmic graveyard that persists forever? Or is this immense quiet merely the prelude to an even more radical transformation? While the last cinders of ordinary matter drift in eternal cold, the fate of its invisible partner is even more elusive. Dark matter, the ghostly scaffolding of the cosmos, faces a future defined by its own profound indifference. This mysterious substance, which outweighs all the stars and galaxies we see by a factor of 5 to 1, feels only the force of gravity. It does not collide, it does not glow, it does not clump into dense balls to become dark stars or dark planets. It is a silent, pervasive haze, a cosmic background actor that only reveals itself by the way it bends the paths of light and dictates the spin of galaxies. Because it ignores light and electromagnetism entirely, dark matter cannot do what ordinary matter does. It cannot cool down by radiating heat, it cannot form complex structures, and it cannot ever shine. So as the grand cosmic structures we see, the galaxies and clusters, are slowly pulled apart by dark energy's expansion, the dark matter halos that hold them together will simply stretch and fade. Picture a vast, invisible cloud of particles, each one isolated and non-interacting, suspended within a balloon that is being inflated faster and faster. The particles do not vanish, but the space between them grows without end. Their density, the number of particles in any given volume, plummets towards zero. The gravitational glue that once bound entire clusters of galaxies together becomes weaker and weaker, until it is no longer strong enough to counteract the relentless push of expansion. On the scale of our future galactic island, the local gravitational influence of dark matter will eventually become negligible, a faint whisper lost in the growing silence. Yet the story of dark matter may not be one of pure, quiet dilution. Some theoretical models suggest that dark matter particles, while stable over the current age of the universe, might not be truly eternal. Certain proposed particles could, over timescales that dwarf even proton decay, spontaneously decay into bursts of gamma rays or pairs of ordinary particles. Others might slowly annihilate upon contact with each other, a process that would release energy as a faint, uniform glow across the cosmos. If such processes are real, they would represent a slow leak in the dark matter reservoir, a gradual conversion of this invisible mass into subtle forms of radiation. However, our most sensitive searches have found no evidence for this. The dark matter halos we observe appear stable and unchanging, giving no signal of such decay or annihilation. For now, the most likely forecast is one of infinite thinning. Dark matter will become a perfectly diffuse, ever more perfect vacuum, its particles so hopelessly isolated from one another by the stretching void that they might as well be alone in the universe. Its final role is passive but profound. Even in its extreme dilution, dark matter's remaining mass energy will continue to shape the geometry of the cosmos itself, influencing the very rate of expansion in a fading background hum. This leaves us with a universe simplifying toward an elemental state, where the only active force is the expansion of space itself. But if both matter and dark matter are destined to fade or dilute, what becomes of the energy they leave behind and the very structure of space-time they once inhabited? This final state has a name, the heat death of the universe. It is not a violent end, but a quiet one, the ultimate stillness. Picture that last cup of coffee in a perfectly insulated room, left alone for eternity. It does not freeze or boil, it simply, slowly reaches the exact same temperature as the air around it. Once that equilibrium is achieved, nothing else happens. No warmth flows from the cup to the room, no energy moves at all. It is a state of perfect, uniform sameness, where no work can be done because there are no differences, no gradients to drive any process. This is the principle of maximum entropy, the final victory of disorder in its most profound sense. In our cosmic story, the coffee cup is the entire universe. The stars were once brilliant points of intense heat against the cold dark, creating the gradients that powered cosmic evolution, but they have all faded. The black holes, those immense wells of gravity, have evaporated. The protons within the last dark remnants may have finally decayed. All that remains is a thin, cold soup of fundamental particles and radiation, stretched by the relentless expansion to undetectably low energies. Every corner of this future cosmos will be the same temperature, a fraction of a degree above absolute zero, with no hotspots, no dense regions, no structure whatsoever. It is a homogeneous void, dark, silent, and unchanging. This fate is not a guess. It is the logical conclusion drawn from applying the second law of thermodynamics to an ever-expanding universe dominated by dark energy. The second law states that the total entropy or disorder of an isolated system always increases over time. Our universe, by definition, is the ultimate isolated system. There is no outside, so all the beautiful, complex structures we see, from swirling galaxies to living planets, are temporary pockets of localized order, paid for by increasing the overall disorder of the cosmos. We are the eddies in a flowing river, intricate patterns that exist only because the water is moving downhill toward a flat, motionless sea. The expansion, driven by dark energy, is what ensures the river reaches that sea. It dilutes everything, smoothing out all temperature and density differences until nothing is left to drive a single engine of change. The arrow of time itself, the reason we remember the past and not the future, is tied to this increase in entropy. In the era of heat death, when entropy has reached its maximum possible value, the arrow of time loses its direction. With no processes occurring, no energy flowing, there is no meaningful difference between one moment and the next for 1 trillion years, or 1 trillion. While this vision may seem bleak, it provides a profound framework for our entire cosmic narrative. It frames the history of the universe from the hot, dense, low-entropy Big Bang to the cold, dilute, high-entropy future as a single, irreversible journey. The dazzling age of stars, the formation of planets, the rise of life, all of it represents a fleeting but magnificent phase in this grand thermodynamic story, a temporary spark of complexity in the long slide toward equilibrium. It asks us to consider not just what remains, but what the journey itself means. But heat death is not the only possible finale written into the laws of physics. There exists a far more dramatic alternative, a cosmic fate that trades an eternity of cold silence for a single, violent crescendo. This scenario is known as the Big Rip. Its premise is terrifyingly simple. What if dark energy is not a constant, gentle push, but a force that grows stronger over time? In this model, the acceleration of the universe's expansion does not merely continue, it feeds upon itself, increasing at an exponential and unstoppable rate. The repulsive power of dark energy would grow so immense that it would not just pull galaxies apart, it would begin to overpower every single force that holds anything together. The stretching of space itself would become the dominant power in the cosmos, overwhelming gravity, then electromagnetism, and finally, the very nuclear forces that bind atomic nuclei. Imagine the universe as a vast, intricate tapestry. In the heat-death scenario, the tapestry hangs forever, its threads fading but remaining intact. In the Big Rip, a hand grabs each edge of that tapestry and pulls with ever-increasing, infinite force. First, the large-scale patterns unravel. The gravitational bonds holding clusters of galaxies together would snap. Next, the individual galaxies themselves would be shredded, their stars flung into the void. But the horror and the awe of this scenario lies in its final moments. As the expansion rate rockets toward infinity within a finite window of time, the violence would reach down to the smallest scales. A star system like our own would be torn apart. The sun's gravity would be rendered meaningless, and Earth would simply drift away into the stretching dark. But it would not stop there. The planet itself would be pulled apart, the gravitational glue holding rock and metal together overcome. Mountains would disintegrate. Then the molecules that form the air and the oceans would be ripped asunder as the electromagnetic forces binding atoms into molecules fail. In the last fraction of a second, the atoms themselves would be shredded. The nuclei of every element would be torn apart, protons and neutrons dissolving into a spray of quarks and energy. In an instant, all structure in the universe would be erased, not by decay or dilution, but by a single, catastrophic tearing of the fabric of reality itself. Whether this fate awaits us hinges on a single, still unknown number, a parameter physicists call the equation of state of dark energy. This number describes the relationship between the pressure dark energy exerts and its density. If this value is exactly -1, dark energy is a constant, leading to the long, slow heat death we discussed. But if it is more negative than that, if the pressure is even more powerfully repulsive, then dark energy's strength grows as the universe expands, setting the stage for the Big Rip. Current observations from telescopes studying the large-scale structure of the cosmos and the cosmic microwave background gently point toward the constant value, favoring the quiet fade over the violent end. Yet the measurements are not yet precise enough to rule out the more dramatic possibility entirely. The Big Rip remains a valid, haunting alternative written into the equations. It serves as a powerful reminder that the ultimate fate of all matter and energy is not yet a settled story. It is a question mark written in the dark, its answer waiting to be found in the precise nature of the universe's most mysterious component. The quiet finality of heat death is not the only story the universe could tell. Before the discovery of dark energy, cosmologists seriously considered a dramatically different ending, one where the expansion was only a temporary phase. This was the idea of the Big Crunch. Picture the entire cosmic expansion run in reverse. Instead of galaxies drifting apart forever, the collective gravity of all matter in the universe, acting like a cosmic brake, would gradually slow the expansion to a halt. Then it would begin to pull everything back together. Distant galaxies whose light is now stretched and redshifted would begin to blueshift as they rushed toward one another. The temperature of the cosmic background radiation, that faint relic of the Big Bang, would begin to rise. As the collapse accelerated, space itself would contract, squeezing the universe into a smaller, hotter, and denser state. Galaxies would merge in violent collisions, stars would be packed so tightly they would rip each other apart, and eventually, all matter and energy would be compressed back into a single, unimaginably hot and dense point, a singularity mirroring the conditions from which our universe was born. This was not merely an end, but a potential reset button for reality. The elegant symmetry was compelling, a universe that breathed in a grand cycle, expanding and contracting. This idea of a cyclical cosmos is ancient, found in many philosophical traditions, but the Big Crunch gave it a modern scientific framework. It suggested the universe might be like a cosmic phoenix, dying in fire and chaos only to be reborn from the ashes in a new Big Bang, starting the story all over again. In such a model, time itself might be cyclical, with each universe inheriting some imprint or echo from the one before, perhaps even preserving information in some transformed state across the cycles. It offered a narrative of eternal return, a universe without a true beginning or end, only an endless rhythm of creation and dissolution. This was a profoundly more optimistic vision than a cold, eternal fade to black. However, the discovery of dark energy and the accelerating expansion presented a major problem for this beautiful idea. Our measurements show the density of ordinary and dark matter is simply not high enough to overcome dark energy's repulsive push. Gravity is losing the tug of war on the largest scales. The brakes have failed and the cosmic engine is accelerating. A simple Big Crunch driven by matter's gravity alone now seems off the table. Yet the human imagination and theoretical physics are not so easily confined. Scientists have explored more sophisticated models where a cyclic universe could still be possible, even with dark energy in the picture. Some ideas from string theory, for example, involve our universe as a three-dimensional membrane or brain floating in a higher dimensional space. Collisions between such brains could trigger Big Bang-like events, not from a singularity, but from the immense energy of the impact, potentially setting off a new cycle of expansion and cooling. Another fascinating proposal is conformal cyclic cosmology, put forward by physicist Roger Penrose. It suggests a way for a universe that has expanded into an almost featureless, empty state to become mathematically identical to the hot, dense singularity of a new Big Bang. In this model, when all matter has decayed into light and particles have lost their mass through extreme expansion, the universe simplifies to a state with no meaningful scale. This scale-free or conformal end can be seamlessly joined to the scale-free beginning of a new universe. It is a profound and poetic idea where the ultimate heat death of one cosmos becomes the smooth, low-entropy starting point for the next. In Penrose's vision, faint imprints of black hole collisions from our universe might even appear as ring-like patterns in the cosmic microwave background of the next cycle, a ghostly signature passed between cosmic generations. These theories are highly speculative, far from proven, but they serve a crucial purpose. They expand our imagination of what is possible. They remind us that our current understanding, based on the universe we can observe, may not capture the full story of eternity. Perhaps the fate of matter and energy is not a one-way trip to silence, but a transformation into the raw material for a new beginning. The cosmos may have more than one ending in its library of possibilities, and some of those endings are also beginnings. The silence of the heat death is not a perfect stillness. Underneath the apparent emptiness, at scales so small they defy visualization, the quantum vacuum remains eternally restless. This is not empty space in the classical sense, but a seething sea of potential. According to quantum mechanics, what we call a vacuum is alive with fleeting, spontaneous activity. Pairs of particles and their antiparticle counterparts can wink into existence, borrowing energy from the vacuum itself for a sliver of time before annihilating each other and returning the energy. They are called virtual particles, and while they are ephemeral, their effects are undeniably real. We have measured their influence in subtle shifts in the energy levels of atoms and in a measurable force between two closely placed metal plates in a vacuum, phenomena known as the Lamb shift and the Casimir effect. This proves that even in a perfect void, there is a fundamental, irreducible energy, a baseline hum to reality itself. This vacuum energy is a leading candidate for the simplest form of dark energy, what Einstein called the cosmological constant. If this intrinsic energy of empty space is positive and constant, then it exerts a gentle, repulsive pressure. As the universe expands and more space comes into existence, the total amount of this repulsive vacuum energy increases, driving the acceleration we observe. In this view, dark energy is not a mysterious new field, but a fundamental property of the quantum vacuum itself, woven into the fabric of space-time. It means the engine of cosmic destiny is not some external force, but an inherent feature of nothingness. In the far, far future, this quantum simmer could become the only show in town. After the last black dwarf has cooled to absolute zero and the final proton has perhaps decayed, the universe will be a vast, cold, and nearly perfect vacuum. Yet, even then, the quantum rules will not sleep. Virtual particles will continue their endless dance of creation and annihilation in the darkness. With no stars or matter to provide competing energy, these quantum fluctuations may become the dominant remaining activity in the cosmos. On timescales that stretch beyond any meaningful measure, this could give rise to entirely new, low-energy quantum phenomena we cannot yet predict, subtle ripples in the fabric of a frozen reality. More speculatively, this eternally active quantum vacuum could hold the seeds for an entirely new beginning. Some models of eternal inflation suggest that our entire observable universe is just one bubble in a vast, eternally expanding multiverse. In such a framework, even in the cold, empty future of our bubble, a rare and enormous quantum fluctuation could trigger a process called quantum tunneling. This would be a spontaneous, random event where a tiny region of our dead vacuum suddenly transitions into a different, high-energy state. If that happened, it could ignite a new inflationary Big Bang, birthing an entirely new universe with its own laws and constants from the ashes of our own. It would be a Genesis event with no cause, arising purely from the probabilistic rules of quantum mechanics given infinite time. This transforms our view of the final fate from a static end to a state of profound potential. The heat death may not be a cemetery but a dormant field. The void would not be truly dead but pregnant with possibility, governed by quantum laws that forever allow for the unexpected. It suggests that even at the end of all things, the underlying machinery of reality remains eternally switched on, ticking over in the darkness, waiting on a timescale we cannot comprehend for the next roll of the cosmic dice. These vast timescales are not just abstract numbers, they are the chapters of a cosmic biography. To truly grasp the fate awaiting matter and energy, we need a map of this unimaginable future, a timeline to oblivion that charts the universe's descent from light into darkness. Our current chapter, the one in which we are living right now, is called the Stelliferous Era. This is the age of stars, a time when galaxies glow with the light of nuclear fusion. It is a brilliant but brief period. While it feels eternal to us, this era of shining suns and swirling nebulae will only last for about 100 trillion years. After that, the universe will have consumed most of its available hydrogen fuel, and the lights will begin to go out one by one. What follows is a descent into a much longer, much darker age known as the Degenerate Era. This epoch, which could span from 10 to the 40th years, is dominated by the cold, dense remnants of dead stars. The sky will no longer be lit by fusion, but by the faint, residual warmth of white dwarfs slowly cooling into black dwarfs and the occasional flicker from colliding stellar cinders. It is a universe in retirement, where the primary activity is the slow, gravitational dance of these dark objects in an ever-expanding, ever-colder void. The Degenerate Era is a museum of what once was a quiet holding pattern that lasts for a duration so long it makes the entire age of stars seem like the blink of an eye. If black holes are the final monuments, then the next chapter belongs to them alone. Sometime around 10 to the 100 years from now, the universe enters the black hole era. By this time, even the last black dwarfs have cooled to near absolute zero. The only significant sources of energy left in the entire cosmos are the evaporating black holes, glowing faintly with Hawking radiation. Each one is a slow leaking clock, ticking down over eons as they convert their immense mass back into a thin spray of particles and light. In this era, a single solar mass black hole shining in the darkness would be like a brilliant city compared to the utter blackness around it, yet its light would be so redshifted and faint it would be nearly impossible to detect. This epoch is defined by evaporation, a universe patiently waiting for its most formidable structures to dissolve. Finally, if proton decay is real, the cosmos transitions into its last conceivable state, the dark era. This begins sometime after 10 to the 40 years, once the last black holes have evaporated and the final stellar remnants have faded. Here, the last possible transformations occur. Any remaining protons, the very bedrock of atomic matter, may finally decay, turning the last specks of solidity into a diffuse mist of radiation and fundamental particles. With this, all structure vanishes. The universe achieves maximum entropy, a state of perfect uniform equilibrium. The temperature is the same everywhere, a fraction of a degree above absolute zero, with no gradients, no flows, and no processes left to mark the passage of time. This is the heat death in its ultimate form, and this dark era is not merely long, it is effectively forever, a silent, unchanging expanse where the expansion of space is the only remaining fact. This chronological framework does more than just list dates. It reveals the fleeting, precious nature of our current cosmic moment. The brilliant stelliferous era, with its galaxies and stars and planets, is the shortest major chapter in the entire story. We exist in a flash of cosmic light, a temporary island of complexity in an ocean of time that leads inevitably toward simplicity and silence. Every process we have discussed, from the redshifting of light to the evaporation of black holes, unfolds across these epochs at a pace utterly alien to human experience. It is a reminder that the universe operates on a schedule written in magnitudes of time we can write down but cannot truly feel. A schedule where the fate of all matter and energy is to slowly, inexorably, return to the dark, quiet vacuum from which it once spectacularly emerged. But the universe's final story is not just about matter and energy, it is also about information. Every particle, every star, every living being is a complex arrangement of data, a specific configuration of matter that tells a story about its history and its state. According to the bedrock principles of quantum mechanics, this information is never supposed to be truly destroyed. It can be scrambled, transformed, and rendered utterly unrecognizable, but it should, in principle, always be preserved in some form. This is a sacred rule called unitarity, and it is central to our understanding of reality. Yet, the ultimate fate we have been describing, one where black holes evaporate and matter itself may decay, seems to threaten this rule at the most fundamental level. This conflict is known as the black hole information paradox, and it is one of the deepest puzzles in all of physics. The paradox begins with a simple question. When an object, say a book or an entire star, falls into a black hole, it crosses the event horizon and is lost from our universe. All the intricate information about that object, the specific arrangement of its atoms, its history, its identity, is seemingly sealed behind a one-way curtain. Then, over eons, the black hole evaporates via Hawking radiation. But Stephen Hawking's original calculations suggested this radiation was purely thermal, a formless, random heat. It contained no specific details about what fell in. If the black hole evaporates completely, leaving behind only this generic glow, then the information about everything it ever consumed appears to be permanently erased from reality. This is the paradox. Information seems to vanish, violating a core tenet of quantum theory. Physicists have wrestled with this for decades, and the proposed solutions are as mind-bending as the problem itself. One leading idea is that the information is not lost at all, but is somehow encoded on the surface of the event horizon, the point of no return. In this view, the horizon acts like a scrambled, chaotic hard drive, storing the data of everything that falls in. Then, as the black hole evaporates, this information is slowly and chaotically imprinted onto the outgoing Hawking radiation. By the time the black hole is gone, all the information has been leaked back out, albeit in a form so complex and mixed that it is practically impossible to decode. It would be like burning a library full of unique books. The information is not gone. It is transformed into the specific pattern of smoke and ash, a pattern that is theoretically reversible but practically indecipherable. Another, even more radical proposal suggests that the information does not escape our universe at all, but instead is funneled into a separate, baby universe that pinches off from our own inside the black hole. In this scenario, the information is preserved, but it is exiled, traveling down a cosmic branch line that we can never access or observe. Then there are ideas that suggest our very understanding of spacetime breaks down at the singularity, and that a future theory of quantum gravity, one that merges Einstein's relativity with quantum mechanics, will resolve the paradox by showing how information is seamlessly transferred. The stakes of this puzzle could not be higher for our cosmic story. In the long-term fate of a dark energy-dominated universe, every single black hole will eventually evaporate. If information is truly lost in that process, then the final state of the cosmos is not just one of maximum entropy and stillness, but one of fundamental amnesia. The universe would forget its own history. The specific quantum details of every star, every planet, and every particle that ever existed would be irretrievably erased from the fabric of reality. The heat death would then represent not just a thermodynamic end, but an informational one. Conversely, if information is always preserved, even through black hole evaporation and proton decay, then the cold, dark, uniform void of the far future is not a blank slate. It is a vast, quiet archive. Every bit of data from 14 billion years of cosmic evolution, from the first stars to the last thinking minds, would still be there, imprinted onto the quantum state of the remaining photons and particles, woven into the very geometry of spacetime itself. It would be a history written in a language we cannot yet read, preserved for an eternity with no one left to read it. This ties the expansive fate of the cosmos directly to the deepest principles of physics. The question of whether information survives forever or eventually fades is a question about the ultimate nature of reality, a clue waiting in the silent future of the universe that might one day guide us to a complete theory of quantum gravity. Our existence in this fleeting era of light is not a random accident, but a necessary clue. We could not have awakened in the silent, cold expanse of the dark era, nor in the searing, featureless plasma of the universe's first moments. We are here thinking about cosmic fate precisely because the conditions around us allow for planets, chemistry, and life. This simple yet profound observation is known as the Anthropic principle. It suggests that any universe we can possibly observe must have properties suitable for the existence of observers. We are not watching the cosmos from a neutral balcony. We are participants on a stage that must, by definition, support actors like us. This reasoning helps answer a haunting question about the expansive fate we have traced. Why does dark energy have the specific, surprisingly small strength that we measure? If it were significantly stronger, the acceleration would have begun so early in cosmic history that galaxies and stars could never have formed. The universe would have been ripped apart before any structure could coalesce. If it were much weaker, gravity might have pulled everything back together in a big crunch long before life had time to emerge on any world. The value we observe seems oddly fine-tuned, sitting in a narrow window that allows for billions of years of cosmic structure building. The anthropic perspective offers a lens. In a vast multiverse where different regions may have different physical constants, we inevitably find ourselves in a bubble where those constants allow for our existence. We measure dark energy's gentle push not because it is the only possible value, but because it is a value that permits galaxies, stars, planets, and ultimately, curious minds to ponder it. This places humanity in a poignant and specific position in cosmic history. We are not at the beginning or the end, but in the middle of the story, during the brief, vibrant chapter where the universe is complex enough to produce life, yet still young enough for us to see evidence of its past and forecast its future. We are transient witnesses to the grand narrative of matter and energy, living in the golden hour between the dawn of creation and the long twilight ahead. Our very ability to ask these questions, to map the timeline to oblivion, is a testament to the special, temporary conditions of this cosmic epoch. We are the universe for a fleeting moment, becoming aware of itself and its own expansive destiny. The ultimate fate of the cosmos is not a philosophical debate, it is a measurement problem. To know where the universe is headed, we must precisely track how fast it is expanding now and how that speed has changed across billions of years. This requires cosmic detective work of the highest order, using the universe itself as both the crime scene and the witness. Astronomers have built a toolkit for this investigation, relying on three powerful techniques that serve as the pillars of modern cosmology. The first are standard candles, celestial objects with a known intrinsic brightness. By measuring how dim they appear from Earth, we can calculate their distance with remarkable accuracy. The most famous of these are Type 1, a supernova, the thermonuclear explosions of white dwarf stars. Because they all reach roughly the same peak brightness, they act like identical light bulbs strung across the cosmos. When two teams used these supernovae in the late 1990s, they were expecting to measure a universe slowing down. Instead, the distant supernova were fainter than predicted, meaning they were farther away than a coasting universe would place them. This was the direct, observational evidence that the expansion is accelerating, the clue that won the Nobel Prize and introduced us to dark energy. The second technique uses standard rulers. Imagine you could freeze the universe just a few 100,000 years after the Big Bang. At that moment, the cosmos was a hot, dense plasma, rippling with sound waves from the primordial pressure of matter and radiation. These waves traveled outward until the universe cooled enough for atoms to form, freezing the waves in place as a subtle, preferred scale imprinted on the distribution of matter. This fossilized echo is called baryon acoustic oscillations. Billions of years later, we can see this scale stamped into the clustering of galaxies. By measuring the apparent size of this standard ruler at different cosmic epochs, we can trace how the geometry of space has stretched over time. It is like finding a ruler of known length embedded in the cosmic web and seeing how its markings appear to us from different distances, giving us another independent check on the expansion history. The third and perhaps most profound pillar is the cosmic microwave background, the afterglow of the Big Bang itself. This faint microwave light is a snapshot of the infant universe, a baby picture from when it was only 380,000 years old. Tiny temperature fluctuations in this light are a treasure map, encoding the amounts of ordinary matter, and dark energy, as well as the overall geometry of the cosmos. By studying this snapshot with exquisite precision, missions like the Planck satellite have provided our most stringent constraints on the cosmic ingredients, telling us that dark energy makes up about 70% of the universe's total energy budget. These three methods, supernova, baryon acoustic oscillations, and the cosmic microwave background, do not work in isolation. They cross-check each other, building a consistent, triangulated story of an accelerating universe dominated by a mysterious repulsive force. This story is far from finished. A new generation of observatories is now taking the stage, designed to probe dark energy with unprecedented precision. The Dark Energy Survey meticulously mapped hundreds of millions of galaxies, measuring their shapes and distributions to trace the invisible hand of dark matter and the repulsive push of dark energy. The James Webb Space Telescope peers back to the universe's first galaxies, helping us understand how structure formed and how dark energy's influence has evolved. Soon, the Vera C. Rubin Observatory will begin a 10-year survey of the entire southern sky, discovering billions of new galaxies and millions of supernova, providing a statistical powerhouse of data that will refine our measurements to a razor's edge. The goal of all this effort is to pin down a single, crucial number, the equation of state of dark energy. This parameter describes the relationship between the pressure dark energy exerts and its density. If it is exactly -1, dark energy is a constant, leading to the long, gentle heat death. If it is more negative, dark energy grows stronger over time, setting the stage for a big rip. Current data strongly favors the constant, quiet fade, but the error bars have not yet closed completely. Every new supernova, every mapped galaxy cluster, every subtle distortion in starlight is a data point narrowing those error bars, testing whether dark energy has changed over the cosmos's lifetime. This transforms cosmology from a theoretical exercise into a live, empirical science. We are not just predicting the future, we are actively measuring the engine that drives it. Each observation is a sentence in a story that is still being written, a story where our deepest assumptions about the fate of all matter and energy are challenged and refined by the cold, hard light of evidence from the sky. This cosmic forecast forces a profound confrontation with the idea of meaning itself. If all structure fades and every story is eventually erased by the silent tide of expansion, does anything we do truly matter? The universe's apparent trajectory toward a cold, empty equilibrium can feel like the ultimate negation, rendering all human effort, creativity, and love into temporary noise against an infinite backdrop of silence. It is a natural, deeply human response to wonder if purpose can exist in a cosmos that forgets. Yet, this very confrontation can unlock a perspective that is not bleak, but strangely liberating. The inevitable fade does not diminish our moment, it illuminates its staggering rarity. Think of the entire cosmic timeline as a vast, dark night. The stelliferous era, this age of stars and galaxies where life can arise, is not the night itself. It is a single, brilliant lightning flash that illuminates the landscape for one breathtaking instant. We are born in that flash. Our entire history, all of art and science and civilization, every joy and struggle, exists within that fleeting illumination. The fact that the night is long and dark does not make the flash any less real, any less beautiful, or any less significant. In fact, it makes it precious beyond measure. Our temporary cosmic stage is not a flaw. It is the necessary condition for anything interesting to happen at all. A universe in perfect, eternal heat death is one where nothing ever happens. A universe that collapses instantly is one where nothing complex can form. We exist in the narrow, golden window between these two monotones, in the sliver of time when the universe is old enough to have forged complex atoms in stellar furnaces, yet young enough to still hold onto the energy gradients that power planets and minds. This context reframes the question of legacy. Perhaps meaning is not found in etching our names onto a cosmos that will outlast them, but in the quality of the etchings we make while the stone is still soft. The pursuit of knowledge, the experience of beauty, the connections we build with one another, these are not negated by a distant future. They are amplified by their transience. They are the vivid patterns in the lightning flash. Consider the simple act of understanding the universe's own story. The hydrogen atoms forged in the first few minutes after the Big Bang have, over billions of years, swirled into stars, planets, and eventually into the neural networks of a species curious enough to trace them back to their origin. The universe has, in us, begun to comprehend itself. This self-awareness is a triumph of matter and energy so improbable, so wondrous, that its temporary nature is almost beside the point. The story is being told, and we are both its characters and its readers. This invites a shift from seeking meaning in eternal endurance to finding it in depth of participation. The cosmic narrative does not demand that we be permanent. It only offers us a role. Our endeavors, from building a family to launching a telescope to creating a work of art, are meaningful because they contribute to the richness of this chapter. They add to the complexity and beauty of the flash. In a universe destined for simplicity, every act of genuine complexity is a quiet rebellion against the eventual silence, a celebration of the temporary conditions that allow such things to be. Our brief tenure is not a sentence of irrelevance, but an invitation to engagement. We are here now during the hospitable epoch. We can look up, decode the light from dying stars, and piece together the epic of space and time. We can look around and forge bonds that matter within the story. This frames human existence not as a futile speck, but as a conscious, meaningful part of an epic journey. We are the universe's way of experiencing its own grandeur and contemplating its own fate. And in that contemplation, even faced with a forecast of cold and dark, we find a reason to make the light we have shine all the brighter. That hydrogen atom's journey is the ultimate cosmic biography. Born in the searing heat of the Big Bang, it spent millions of years as a free particle, drifting through the primordial darkness. Then, drawn by gravity into a collapsing cloud of gas, it was swept into the core of one of the universe's first stars. There, under unimaginable pressure and temperature, it was fused with another hydrogen atom, its identity merging to form helium. In that violent act of fusion, a tiny portion of its mass was converted directly into energy, streaming outward as photons to eventually warm distant worlds. This is the first great transformation, from matter into pure radiation, powering the star's brilliant life. When that first-generation star reached the end of its life, it did not fade quietly. It exploded in a cataclysmic supernova, an event so powerful it forged even heavier elements like carbon, oxygen, and iron. Our atom, now part of a heavier element, was blasted back into the interstellar void. For eons it drifted until the gravitational pull of a new, swirling cloud of gas and dust drew it in. This time it was not destined for a stellar core, but for the cooler, quieter outskirts of a forming solar system. It became part of a molecule in a cloud that coalesced into a rocky planet, perhaps even becoming part of a mountain or an ocean on a world orbiting a stable, long-lived star. For billions of years it rested there, a silent participant in geological ages, but its journey was far from over. In the distant degenerative era, long after that star has died, the planet may be shattered or consumed. Our atom could be flung into the cold interstellar medium once more. Its ultimate fate branches into possibilities dictated by the expansive stage. It might be captured by the intense gravity of a neutron star or a black hole, crossing an event horizon to have its information scrambled and stored. Or if proton decay is a law of nature, it may experience the most fundamental transformation of all. Deep in the cold heart of a black dwarf, the proton at the center of its nucleus could spontaneously decay, breaking apart into lighter particles and gamma rays. In that instant, the matter that had been forged in a star and woven into a planet is converted completely and finally back into radiant energy. This entire epic from fusion to decay highlights a profound truth. Matter is not a permanent substance. It is a temporary configuration of energy, a frozen knot in the fields that make up reality. Fusion, fission, gravitational capture, and decay are all just processes that untie and retie that knot, changing the state of the energy but not destroying it. According to the great pillars of physics, general relativity and thermodynamics, the total energy content of the universe is conserved or redistributed, even as the space containing it stretches. The energy from that primordial hydrogen atom never disappears. It merely changes form from mass to light, from order to disorder, always flowing downhill toward equilibrium. This reveals the universe as a place of constant dynamic reshaping. Local forces like gravity and nuclear physics create temporary islands of complexity, like stars, planets, and life. But these are eddies in a vast river flowing toward a silent sea. The global expansion, driven by dark energy, is the current that ensures the river eventually becomes still. Recognizing the impermanence of every atom does not diminish the story. It makes the intricate, beautiful configurations we see today all the more remarkable. We are witnessing a fleeting masterpiece of energy in transformation, a dance of form and dissolution on the grandest possible stage. The most brilliant supernova would eventually fade into a whisper, but light is not the only thing that dims. Every form of energy in the cosmos is subject to the same relentless dilution by the expanding stage. Think of the universe as a container that is constantly, and now acceleratingly, growing larger. If you pour a fixed amount of energy into that container, its density, its concentration must inevitably thin out. This is the universal fading of all signals, a slow draining of vigor that touches everything. The cosmic microwave background, that faint afterglow of creation, is the perfect example. When it first burst forth, it was a blistering sea of high-energy gamma rays. Over billions of years, the expansion of space has stretched those photons, lowering their energy into the microwave range we detect today. This cooling is not a one-time event, but a continuous process. In the far future, those same photons will be stretched into even longer, lower-energy radio waves, until their individual energy becomes so negligible they blend into an undetectable background hum. Even the kinetic energy of particles, the energy of motion from galaxies swirling or gas clouds colliding, faces this fate. As structures are pulled apart and interactions become rarer, this bustling motion slows toward stillness, its energy dissipated across a vaster volume. This raises a subtle but crucial point about matter itself. The famous equation tells us that mass is a form of energy, locked away in the structure of particles. The expansion does not destroy this rest mass energy. A proton's inherent energy remains invariant, but its influence, its gravitational pull, weakens dramatically with dilution. Gravity depends on density, on how much mass is packed into a given volume. As the universe expands and matter is spread ever more thinly, the gravitational attraction between distant particles becomes vanishingly small. So while the intrinsic energy of matter remains, its ability to do anything, to clump together and create new structures, is steadily eroded. It is like having a vast treasure of gold, but each coin is flung to a different corner of an ever-growing desert, too far apart to ever be collected again. The treasure exists, but it is functionally lost. In a universe accelerating under dark energy's push, this process reaches its logical and profound conclusion. Regions of space that are not already bound by gravity will be carried apart at speeds that forever prevent any communication. Light or any other signal from one region can never reach another. The observable universe from any given point shrinks to a finite island of causality, utterly isolated from all others. Within each isolated island, the final act of thermodynamics plays out. Any remaining local differences in energy, the last hot spots near a cooling stellar remnant or the final eddies of particle motion, will slowly and irreversibly smooth out. Energy will flow from areas of higher concentration to lower until everything is exactly the same temperature. Once that perfect uniformity is achieved, no further work is possible. You cannot run an engine if there is no temperature difference to drive it. You cannot extract useful energy from a perfectly smooth gradient. The universe reaches a state of maximum entropy, not because energy has vanished, but because it has become so perfectly and uniformly spread that it is effectively unusable. It is a static equilibrium, a cosmic tableau where everything that can happen has happened, and all that remains is the silent, unchanging fact of expansion itself. This is the thermodynamic end of the cosmic story, where energy exists everywhere but accomplishes nothing, a permanent and universal stillness. The persistence of life is a quiet rebellion against the cosmic slide toward disorder. On a frozen world orbiting a long dead star, the last outpost of a civilization huddles not around a sun, but around the deep geological warmth of its planet's core. Radioactive elements forged in ancient stellar explosions continue their slow decay, providing a faint trickle of heat. Or perhaps the world is a moon, gripped by the gravitational embrace of a gas giant, its interior churned and warmed by relentless tidal forces. In such places, liquid water could persist in subsurface oceans, shielded by miles of ice from the absolute cold of space above. These dark, abyssal realms could harbor life long after the last star in the sky has faded to a black dwarf. The energy gradients here are subtle, not the roaring fusion of a sun, but the gentle, persistent heat from a planet's slow cooling or a moon's rhythmic flexing. Life in its most tenacious forms might cling to these gradients, a whisper of biochemistry in the permanent night. Yet even this refuge has an expiration date. Radioactive elements decay into stable forms, their heat output dwindling to nothing. Tidal forces slowly circularize orbits, damping the internal friction that provides warmth. The energy gradients, however faint, will eventually smooth out. When they do, the last liquid water will freeze, and the final metabolic processes will grind to a halt. Life as a process that locally reduces entropy by consuming energy from its surroundings cannot exist in a state of perfect equilibrium. It is a fire that must be fed, and in the degenerative era, the fuel simply runs out. This paints a startling portrait of intelligence in the deep time of the cosmos. Any civilization that arises and survives its own technological adolescence would face a universe of dwindling resources. Imagine a society billions of years more advanced than our own, witnessing the last stars flicker out. Their grand projects would turn from starflight to energy husbandry. They might learn to harness the last great sources, perhaps by carefully feeding matter into the accretion disks of stellar mass black holes, extracting energy with near-perfect efficiency. Or with patience spanning eons, they could cultivate the Hawking radiation from those same black holes, using them as cosmic batteries that slowly discharge over astronomical timescales. Such a civilization would be the ultimate archivists and engineers, stretching every joule of usable energy across millennia. Yet, the second law of thermodynamics is an unbreakable warden. No matter their ingenuity, they would be fighting a rearguard action against the inevitable. Every conversion of energy produces waste heat, increasing entropy. Their vast, cold computers, their preserved archives, even their own conscious thoughts, would all be processes that require energy gradients to function. In a universe marching toward maximum entropy, those gradients are a finite and non-renewable resource. The final, most profound limit any intelligence would face is not a lack of knowledge, but a lack of difference, a lack of anywhere for energy to flow from and to. The last thought in the cosmos would not be one of despair, but perhaps of quiet acceptance, as the system required to sustain any thought at all finally, peacefully, winds down. This realization frames our current epoch not as mundane, but as miraculous. The era of biological and technological complexity is not the default state of the universe. It is a spectacularly rare phase. We exist during the cosmic springtime when hydrogen is plentiful, stars are bright, and energy cascades through the galaxy in forms life can capture. It is a narrow window bracketed by a sterile, searing beginning and a silent, frozen end. Within this window, matter has briefly become intricate enough to wonder about its own fate. This perspective does not diminish our story, it concentrates it with a poignant urgency. Every act of curiosity, from planting a garden to launching a probe to a distant world, is a celebration of this temporary abundance. Our drive to explore, to understand, to connect, is the universe's own brief flowering of self-awareness. We are not latecomers to a finished cosmos, we are witnesses to its most dynamic act. And in understanding that this act has a final curtain, we are given the clearest possible reason to pay attention, to learn everything we can, and to make the light of our consciousness shine while the stage is still set for drama. This leads us to a final, humbling frontier, not of space but of scale. If our era is a fleeting moment, how can we even begin to measure the true scope of the future that awaits? The ultimate fate of matter and energy may hinge on a physics we do not yet fully possess. Our entire cosmic forecast, from the silent heat death to the violent Big Rip, is built on two magnificent but separate pillars of modern science. On one hand, we have general relativity, Einstein's breathtaking description of gravity as the curvature of spacetime itself. It is this theory that perfectly explains the large-scale expansion of the universe, the bending of light around galaxies, and the nature of black holes. On the other hand, we have quantum mechanics, the wildly successful rulebook for the subatomic world, governing everything from the stability of atoms to the behavior of particles and forces at the smallest imaginable scales. Both theories are spectacularly accurate within their own domains, but they are fundamentally incompatible with each other. General relativity paints a smooth, continuous fabric of spacetime, while quantum mechanics insists that at the tiniest levels, reality is grainy, probabilistic, and subject to wild fluctuations. This conflict means that to truly understand the universe's final state, especially in extremes of infinite density or over infinite time, we need a theory that unifies them, a framework known as quantum gravity. This is not just an academic puzzle, it is the key that could unlock a completely different set of possibilities for how everything ends. Think of it like trying to predict the final shape of an ice sculpture using only the rules for water and the rules for solid ice. You understand the fluidity of the liquid and the rigidity of the solid, but you lack the precise physics of the phase transition itself, the moment of freezing. Our current cosmological predictions are in a similar bind. We use relativity to model the expanding universe and quantum mechanics to predict particle decay, but we have no complete theory for when gravity itself becomes a quantum phenomenon, at the very center of a black hole or in the first instant of the Big Bang. A successful theory of quantum gravity, such as string theory or loop quantum gravity, might radically alter our vision of the far future. For instance, it could show that the classical idea of a singularity, a point of infinite density, is physically impossible. Instead of a true infinity, quantum effects might create a bounce, a moment where collapsing spacetime rebounds into a new expansion. This idea of a quantum bounce offers a potential escape from the heat-death narrative, suggesting a cyclical universe not driven by dark energy's reversal, but by fundamental physics at the Planck scale. At this unimaginably tiny scale, a distance of about 10 to the negative 35 meters, the smooth continuum of spacetime described by Einstein is expected to break down. Quantum gravity suggests that spacetime itself may have a discrete, foamy structure, a seething ocean of virtual black holes and wormholes blinking in and out of existence. In the context of an eternally expanding, nearly empty universe, this quantum foam could become the dominant texture of reality. Over timescales that dwarf even the dark era, the universe's vast, cold vacuum is not truly inert. It is this eternally bubbling quantum sea, and in such a sea, given enough time, an extraordinarily rare event could occur: quantum tunneling on a cosmic scale. A random fluctuation in this foam could, by sheer unimaginable chance, tunnel through an energy barrier and nucleate a new, high-energy vacuum bubble. This bubble would then expand at the speed of light, its interior undergoing a new inflationary Big Bang, birthing an entirely new universe with its own laws of physics. From the perspective of our old, cold cosmos, this would be a spontaneous genesis, a new beginning flowering from the quantum uncertainty of the void. This possibility transforms the meaning of an end. The classical heat death, that state of maximum entropy and eternal silence, might not be a permanent cemetery. It could instead be a metastable state, a valley in a vast cosmic landscape, stable for epochs longer than we can compute, but not for true eternity. Given infinite time, the quantum dice will eventually roll a perfect hand. This means the ultimate fate of all matter and energy in our universe might not be oblivion, but reincarnation into a new cosmic story. Our universe's long journey toward darkness and simplicity could simply be the necessary quiet that precedes a new burst of complexity elsewhere in the multiversal landscape. Exploring these frontiers is humbling. It reminds us that our predictions about the ultimate fate, while based on the best data and theories we have, are still projections from an incomplete map of reality. The true destiny of matter and energy may hold surprises that only a unified theory of quantum gravity can unveil, suggesting that even in the farthest future, the universe retains a capacity for the unexpected, written into the very fabric of space-time at its most fundamental level. Our local universe may be just a single room in an infinite cosmic mansion. This is the startling vision of eternal inflation, a theory that extends the idea of the Big Bang's initial explosive growth into a never-ending process. In this model, the rapid expansion we call inflation did not stop everywhere at once. Instead, it continues eternally in a background sea of high-energy spacetime, a roiling, repulsive medium sometimes called the false vacuum. Within this eternally inflating background, random quantum fluctuations can act like seeds. A tiny region, through a rare quantum jump, can suddenly drop to a lower energy state. This drop releases a tremendous amount of energy, which immediately triggers a new, localized burst of inflation inside that region. The boundary of this region expands at nearly the speed of light, inflating into a huge, self-contained bubble universe, while the eternal inflation outside continues unabated. Our entire observable cosmos, with all its hundreds of billions of galaxies, could be the interior of just one such bubble, a single island of stable physics that cooled and evolved after its own private inflationary episode ended. And if it happened here, it is happening elsewhere, an infinite number of times. The eternally inflating background is constantly giving birth to new bubble universes, a cosmic froth where new realities are always bubbling up. Each of these bubbles may crystallize with different fundamental properties: the strength of gravity, the mass of an electron, the number of spatial dimensions, even the value of dark energy could be randomly set during that phase transition. Some bubbles might have dark energy so strong they rip apart instantly. Others might have gravity so dominant they collapse back in a flash. But in an infinite multiverse of such bubbles, there will inevitably be some where the constants, by sheer chance, fall into the narrow Goldilocks zone that allows for galaxies, stars, planets, and life. In this picture, our universe is not fine-tuned for us. We simply find ourselves in one of the bubbles where the numbers worked out. This transforms the narrative of cosmic fate from a single, tragic storyline into a grand anthology. Our local bubble may be on a one-way journey to heat death, a cold and silent finale for all the matter and energy within it. But the larger multiverse has no such ending. The eternal inflation continues forever, spawning new bubbles without limit. While our story reaches a final page, the library itself has infinite shelves, and new books are being written every moment. This means that stars are being born somewhere, right now, even in a future where our own sky has been dark for trillions of years. Civilizations may be rising, falling, and wondering about their own place in the cosmos in bubbles so distant their light can never cross the inflating gaps between us. The fate of matter and energy is not a universal constant but a local condition. In some bubbles, matter might be eternally stable, forming structures that last forever. In others, it might transform in ways we cannot yet imagine. The heat death of our universe is not the end of everything. It is merely the conclusion of our particular volume in a much greater, potentially infinite meta-reality. This idea, while currently beyond the reach of direct experimental proof, offers a profound philosophical shift. It suggests that absolute finality may be an illusion of perspective. We are like a person in a single, beautiful, but eventually decaying house, unaware that the neighborhood extends without end and new houses are always under construction. Our local destiny is real and inescapable, but it is not the whole of existence. The drama of matter and energy, of structure rising from chaos and then slowly smoothing away, is not a singular event. It is a play performed on an infinite number of stages with infinite variations on the script. Some versions end quickly, others last for eons, but the theater itself never closes. This embedding of our story within a vaster, potentially unending meta-narrative does not make our journey less meaningful. Instead, it highlights the incredible rarity and value of the conditions that allowed our chapter to be written at all. We are witnesses to a specific, temporary configuration of reality, one that allows for questions to be asked and for beauty to be perceived. That we can even conceive of a multiverse, using the laws of physics that govern our own bubble to peer beyond its apparent horizons, is a testament to the extraordinary capacity for understanding that this specific arrangement of matter and energy has for a time produced. The precise nature of dark energy is not a settled fact, but an open question written in the geometry of the cosmos. While the simplest model treats it as Einstein's cosmological constant, a fixed feature of empty space, physicists have woven more dynamic and dramatic possibilities. These alternative models carry names that sound like ancient forces, quintessence, and phantom energy, and they paint radically different portraits of our cosmic destiny. Quintessence imagines dark energy not as a constant, but as a dynamic field that permeates space, a kind of cosmic fluid whose density and pressure can slowly change over billions of years. This fluid could gradually decay, its repulsive push weakening with time. In such a scenario, the acceleration of the universe might not be a permanent sentence. The expansion could eventually slow, or in a speculative twist, the field's value could even flip, turning repulsion into attraction. This opens a door, however narrow, to a future where gravity might reassert itself on the largest scales, potentially altering the long-term forecast from a cold fade to something else entirely. It is a model that retains an element of cosmic suspense, where the final act is not yet written. In stark contrast stands the more ominous phantom energy model. Here, dark energy is not just constant but grows stronger. Its equation of state, that crucial number describing its pressure to density ratio, is less than -1. This seemingly small mathematical difference has catastrophic consequences. Instead of a gentle, constant push, phantom energy's repulsive force intensifies as the universe expands. This creates a runaway feedback loop with a finite, violent conclusion, the Big Rip. In this timeline, the acceleration does not merely isolate galaxies. It actively shreds every bound structure, from galaxy clusters down to atoms themselves within a calculable window of time. The difference between these models is not academic. It is the difference between an eternal, quiet rest and a sudden, total dissolution. So how do we choose between a fading constant, a decaying field, or a growing phantom? The evidence is written in the oldest light we can see and the most distant explosions we can find. By meticulously measuring the cosmic microwave background, the afterglow of the Big Bang, cosmologists can discern the imprint of dark energy on the infant universe's geometry. By charting thousands of distant supernovae, they can trace how the expansion rate has changed over cosmic history, looking for any subtle deviation from the prediction of a simple cosmological constant. So far, the universe's testimony favors the quiet constant. The data from these profound observations tightly constrain the possibilities, suggesting that if dark energy is dynamic, its changes are exceedingly slow. The phantom energy scenario, while not completely ruled out, sits at the edge of what the measurements allow. Yet the uncertainty remains, and it is this lingering mystery that fuels one of the most urgent quests in modern science. Determining the true nature of dark energy is not just about classifying a mysterious component. It is about reading the final chapter of the cosmic story before it is written. The answer dictates whether matter and energy face a slow dilution over uncountable eons, or a definitive, violent transformation in a finite future. It decides the ultimate fate of every structure, from the grandest galaxy to the last proton. Every new observation, every refined measurement of a supernova's faint light or a subtle twist in the microwave background is a sentence in that chapter, bringing us closer to knowing which kind of universe we actually inhabit. The shape of the universe is not just a metaphor, it is a precise geometric question with profound consequences. When cosmologists speak of cosmic topology, they are asking about the large-scale form of all space, the canvas upon which the entire drama of expansion and fate is painted. This shape dictates the ultimate geometry of reality, influencing how light travels across the eons and determining whether the cosmos is infinite or merely boundless. For a long time, three classic possibilities framed the debate. The universe could be flat, like an infinite sheet of paper extending forever in all directions. It could be positively curved like the surface of a sphere, finite in size but with no edge, or it could be negatively curved like a saddle, flaring outward in a hyperbolic shape. Each of these geometries carries a different forecast for destiny. A spherical, closed universe contains enough matter and energy to eventually halt its own expansion through gravity, leading to an eventual recollapse into a big crunch. A flat or hyperbolic, open universe would expand forever, its galaxies drifting apart into an endless, cooling void. For decades, this was the central question, a geometric tug-of-war between gravity and motion. Then came the precise measurements of the cosmic microwave background, the ancient light from the infant cosmos. Those detailed maps of the early universe revealed something remarkable. The patterns of hot and cold spots, the subtle imprints of primordial sound waves, matched the predictions of a flat geometry with extraordinary precision. The data tells us that on the largest scales we can measure, the universe appears to be flat, or so nearly flat that any curvature is too slight for our instruments to detect. This geometric finding, when combined with the discovery of dark energy, locks in a specific long-term forecast. A flat universe with a cosmological constant, a constant dark energy, is set on a one-way path to eternal expansion. There is not enough collective gravity to ever pull everything back together, and the repulsive push of dark energy ensures the expansion not only continues but accelerates. This is the strongest evidence yet for the heat-death scenario, a quiet, infinite thinning of all structure. Yet the story of topology holds a fascinating twist. A flat geometry does not necessarily mean the universe is infinite. it is possible for space to be flat and yet finite, a concept that bends the mind. Think of the surface of a cylinder. It is flat with no intrinsic curvature, but it is finite in one direction and loops back on itself. In 3 dimensions, a flat universe could have a similar toroidal or donut-like shape. In such a cosmos, if you could travel in a perfectly straight line for long enough, you would eventually return to your starting point from the opposite direction, having never encountered an edge. The universe would be finite but unbounded. If this were true, it would have subtle but profound implications for the far future. In an accelerating universe that is infinite and flat, regions are carried apart over horizons, lost to each other forever. But in a finite, flat universe, even as space stretches, the overall connectivity remains. Light from a galaxy, though immensely redshifted and faded, could in principle complete a full circuit of the cosmos over trillions of years, creating ghostly echoes of the past. While this would not prevent the heat death, it introduces a strange kind of closure, a cosmic loop where all history is, in a sense, contained within a finite volume, however vast. Current observations have found no evidence for such a wrapping, no repeating patterns in the cosmic microwave background that would signal we are seeing the same distant regions from different directions. The observable universe appears simply connected, with no visible loops, yet the possibility remains that the universe is so large that any repeating pattern lies beyond our cosmic horizon, forever out of view. This interplay between geometry and expansion adds a crucial layer to our understanding of fate. Topology sets the stage, but dark energy directs the play. Even a spherical universe, which classically points to a big crunch, could have its recollapse prevented or indefinitely delayed if dark energy's repulsive force is strong and persistent enough. The shape tells us about the total energy density, but the nature of that energy determines how the story unfolds on that shaped stage. So when we forecast the ultimate fate of matter and energy, we are synthesizing 2 deep insights: the geometric shape of space from the first light, and the dynamic engine of dark energy from the fading light of distant stars. Together, they sketch a cosmos that is flat, accelerating, and likely destined for a slow, cold, and eternal equilibrium, a final geometric stillness written into the fabric of space itself from the very beginning. This faint, uniform glow is the universe's oldest photograph. The cosmic microwave background radiation is the cooled and stretched afterglow of the Big Bang itself, a snapshot taken when the cosmos was only 380,000 years old. At that moment, the hot, dense plasma of particles and light finally cooled enough for atoms to form, allowing photons to travel freely across space for the first time. Those ancient photons have been traveling ever since, and we now detect them as a whisper of microwave radiation bathing the entire sky, a relic with a temperature of just about 2.7 degrees above absolute zero. It is the most important reference frame we have, a fossilized imprint of the universe's smooth, hot infancy, but this fossil is not static, it is actively cooling. As space expands, the wavelength of every one of these primordial photons is stretched, shifting them to longer, lower energy wavelengths. This is the same cosmological redshift that affects starlight, but applied to the very first light of all. The cosmic microwave background is a cosmic thermometer, and its reading is steadily dropping. In the far future, as the expansion accelerates, this cooling will continue without end. The temperature of this background radiation will approach, but never quite reach, absolute zero. Its photons will be stretched into wavelengths so long, their energy so negligible, that they will fade from detectability entirely. This marks a profound transition in the life of the cosmos. The universe will have lost its most fundamental thermal signature, the last pervasive warmth from its explosive birth. The transition from a hot, dense beginning to a cold, dilute end is written directly in the cooling of this radiation. Yet, within that nearly perfect uniformity lie the seeds of everything. The cosmic microwave background is not perfectly smooth. It contains tiny fluctuations, variations in temperature of just 1 part in 100,000. These minute ripples are the imprint of quantum fluctuations from the universe's first instance, stretched to cosmic size by inflation. They are the gravitational blueprints for all future structure. By studying these patterns with exquisite precision, missions like the Planck satellite have decoded the universe's vital statistics. They revealed the precise amounts of ordinary matter and dark matter, confirmed the flat geometry of space, and provided the first solid evidence for the initial inflationary expansion. This ancient light has already told us what the universe is made of and how it is shaped, but its story may hold even deeper clues. Future, even more sensitive observations might detect subtle distortions in this pattern caused by the early influence of dark energy, or find faint, swirling signatures that could point to gravitational waves from the inflationary epoch itself. Some theories even suggest that imprints from a prior cosmic cycle, or from quantum gravity effects at the moment of the Big Bang, could be encoded in this radiation, waiting for a generation of telescopes advanced enough to read them. Therefore, the cosmic microwave background is far more than a look backward. It is a direct link between the universe's first moments and its ultimate fate. Its relentless cooling is the most direct evidence we have for the expansive, cooling future that awaits. Every photon in that background is a messenger from the hot beginning, and its stretched, faded state today shows us exactly how the engine of expansion dilutes the primordial energy of creation. By tracing its evolution from a blazing afterglow to a cold whisper, we witness the central plot of cosmic history, the irreversible transformation of a fiery, structured beginning into a dark, smooth eternity. This fading relic reminds us that the universe's story is one of energy slowly settling into equilibrium, a process that began with the release of the first light and will end only when that light has been stretched into silence. While light fades into a whisper, another kind of ripple still travels through the stretching cosmos. Gravitational waves are not made of photons, they are literal distortions in the fabric of spacetime itself, generated by the most violent events imaginable. When two black holes spiral together and merge, they do not create a flash of light, they send a shudder through the universe, a wave that compresses and stretches space as it passes. These waves travel at the speed of light, carrying with them the unique signature of their cataclysmic birth. But just like light, gravitational waves are not immune to the expansion of the universe. As space stretches, the wavelength of these spacetime ripples is also pulled longer. This gravitational wave redshift is a direct echo of the process that dims starlight, but it affects a completely different kind of cosmic signal. A high-frequency chirp from a recent black hole merger, detectable by observatories like LIGO today, would, over billions of years, be stretched into an ultra-low-frequency rumble. In the far future, the cosmos will be filled with these deep, slow vibrations, whispers of ancient violence stretched to near stillness by the relentless expansion of time and space. This presents a remarkable possibility. While the light from the first stars and galaxies will eventually redshift into oblivion, vanishing over the cosmic horizon, these gravitational echoes might persist on a different channel. They could carry information from an era otherwise lost to us, a fossil record not written in light, but in the very geometry of reality. Future observatories, perhaps vast arrays of sensors in space designed to detect these ultra-low-frequency waves, might tune into a stochastic background, a cosmic hum composed of countless overlapping signals. This hum could tell stories we can learn no other way. It might contain the collective rumble of the universe's very first black holes, formed from the collapse of primordial gas before any stars had ignited. It could hold the signature of cosmological phase transitions, moments in the infant universe when the fundamental forces themselves split apart, releasing titanic bursts of energy that shook spacetime. This gravitational wave background would provide a parallel narrative to the one told by light, a complementary history of the cosmos written in vibrations rather than photons. The fate of these waves, however, ultimately mirrors that of all energy in an accelerating universe. They are diluted, their amplitude weakening as they spread across an ever-growing volume. Yet, as a form of pure spacetime curvature, they represent something fundamental. They are not something traveling through space, they are a disturbance of space itself. This means that even when the last star has cooled and the electromagnetic sky is perfectly, permanently dark, these ghostly ripples may still, in principle, be traversing the void. They would be a testament to a dynamic, violent youth, the universe's own memory of its formative convulsions, encoded not in fading light but in the silent, stretching geometry of nothingness. This lingering potential highlights a profound duality in how we understand cosmic history, forcing us to listen for the past in the very fabric of the stage, long after the actors have left and the lights have gone out. Our cosmic story reveals a universe destined for simplicity, but our moment is one of profound complexity. This understanding carries a quiet ethical weight, a call to stewardship born not from fear of an imminent end, but from a deep appreciation of our temporary, golden position in cosmic history. Earth's teeming biosphere, with its intricate web of life, is not the universe's default state. It is a rare and fleeting masterpiece, a vibrant anomaly in a cosmos whose overarching trend is toward dispersion, cold, and silence. The resources of our solar system, from the sunlight warming our world to the minerals locked within asteroids, are not infinite, but they represent a concentrated wealth of energy and matter available during this brief, hospitable chapter. Recognizing this cosmic context reframes our responsibility. It suggests that preserving this pocket of complexity, this island of knowledge and biological wonder, is a meaningful act within the grand narrative. It is not about defying the ultimate fate of the universe, which operates on timescales we cannot influence, but about honoring and extending the unique conditions of our epoch for as long as we are able. This perspective does not prescribe a specific political or technological solution. Instead, it offers a foundational ethical framework, a long view that values sustainability, careful exploration, and the patient transmission of culture and science across generations. It asks us to consider our actions not just in terms of decades, but in terms of centuries and millennia, aligning our goals with the longevity of the cosmic window we occupy. When we work to protect the stability of our climate, we are safeguarding the delicate gradients that power our global biosphere. When we strive to use resources wisely and venture sustainably into our solar system, we are expanding the realm of human experience and knowledge, increasing the resilience of our collective project. These endeavors gain a deeper significance when seen as part of a collective human project to nurture and extend the reach of consciousness and understanding. We are the universe for a time becoming aware of itself, our science, our art, our accumulated wisdom, our ways of deepening that awareness, of making the most of the light before the long twilight. In this light, every effort to learn, to create, and to connect becomes part of a meaningful chapter. It transforms our era from a mere prelude to an inevitable darkness into a period of active, purposeful engagement. We are not passive witnesses to cosmic fate, we are active participants in the story of complexity. The choices we make about how we live on this planet, how we explore our celestial neighborhood, and what we choose to pass on to future generations are the substance of this chapter. They are how we write meaning into our fleeting moment of cosmic spring. This long-term ethical vision, inspired by the stars themselves, invites us to see our time not as a small, insignificant blip, but as a precious and responsible tenure, a chance to tend the flame of awareness in a universe that will one day grow very, very cold. Pulling all these threads together, we arrive at a single, coherent forecast. Based on the weight of current evidence, the measured acceleration from dark energy, the principles of thermodynamics, and the predicted lifetimes of particles and black holes, the most likely future for our universe is a long, slow fade into what we call heat death. This is not a sudden event, but an asymptotic approach to a final state. The cosmos will expand forever, growing colder, darker, and more uniform with each passing eon, until all usable energy gradients have been completely smoothed away. It is a forecast of eternal expansion leading to an eternal, silent equilibrium. Yet, within the vast library of theoretical physics, other endings remain on the shelf. The violent crescendo of a big rip is still mathematically possible if dark energy behaves in a specific, phantom-like way. The elegant symmetry of a cyclic universe, whether through brane collisions or conformal recycling, offers a vision of cosmic rebirth. And the quantum potential of the vacuum suggests that even from a state of maximum entropy, a new beginning could spontaneously flower. These are not mere fantasies. They are valid possibilities that await the sharpening blade of future observation. What emerges from this synthesis is not a single, guaranteed destiny, but a powerful overarching theme. Regardless of the specific path, the universe appears to be on a one-way journey from complexity to simplicity. The magnificent, intricate structures we see today, galaxies, stars, planets, and life, are transient phenomena. They are temporary eddies in a river flowing inexorably toward a still, flat sea. Energy, while conserved, becomes so perfectly diluted and evenly spread that it can no longer perform any work or sustain any process. This is the ultimate meaning of maximum entropy, a state where nothing happens because there is no difference anywhere to drive anything to happen. Understanding this forecast is not an exercise in cosmic pessimism. It is the opposite. This scientific extrapolation, grounded in observation and theory, frames our present moment with breathtaking clarity. We exist during the brief, brilliant phase when the universe is complex enough to produce galaxies and minds, yet still young enough for us to trace the light back to its origin. The very fact that we can contemplate this immense future, that we can measure the redshift of ancient light and calculate the half-life of protons, is a testament to the extraordinary, temporary conditions of this cosmic era. The forecast of a cold, dark end does not diminish our story. It concentrates its meaning into the here and now. We are witnesses to the universe's most dynamic act, and in understanding that the curtain will eventually fall, we are given every reason to pay close attention to the performance while it lasts. The universe's final forecast is not a simple ending, but a transformation. We have traced the expansive fate of matter and energy across timelines so vast they defy imagination, from the accelerating push of dark energy to the silent fade of the last photon. This cosmic narrative reveals a profound truth: nothing in the cosmos is permanent. The grandest galaxies, the mightiest black holes, even the very atoms that form the bedrock of reality, are transient participants in a story of constant change. The expansion of space itself is the great director of this slow-motion finale, orchestrating a universe that evolves from brilliant complexity toward a state of ultimate simplicity. Yet within this understanding lies a powerful and unexpected perspective. Knowing that the cosmos is destined for a cold, quiet equilibrium does not diminish our moment, it illuminates its staggering significance. We exist in a fleeting golden age, a narrow window of cosmic time when the universe is old enough to have forged the elements for planets and life, yet still young enough to retain the energy gradients that make such complexity possible. Our ability to look up, to measure the light from dying stars, to calculate the half-life of protons, and to contemplate the universe's ultimate fate, is itself a miraculous product of this ephemeral epoch. We are the cosmos for a brief and brilliant moment, becoming aware of its own story. This awareness invites a deeper curiosity, not just about the distant future, but about the fundamental laws of physics that allow such a story to unfold. It drives us to keep questioning, to keep building better telescopes, and to keep refining our theories, because each new discovery sharpens our view of the cosmic stage and our unique place upon it. Let this exploration be more than a catalogue of endings. Let it be a call to continued wonder. Look up at the night sky with the knowledge that you are witnessing a temporary masterpiece. Share these ideas, discuss them, and let them shape how you view our shared time on this pale blue dot. Our journey to the edge of time reminds us that meaning is not found in eternal endurance, but in the depth of our engagement with the reality we are given. Thank you for joining this voyage through the deepest mysteries of space and time. If these ideas about our cosmic fate resonate with you, consider subscribing for more journeys into the wonders of the universe. We would love to hear your thoughts on this grand narrative in the comments below.